Next, exercise 9. In this one, we are given an index set I, which is any set actually, and such a set is called an index set because its elements are used to label some other things. In this case, the elements alpha in I are used to label some sets. A alpha. Alpha labels A alpha. In this sense, that is, for each alpha in I, A alpha is itself a set, and each such A alpha is given to be at most countable, and our index set I itself is at most countable. That means I is either finite or countable, and for every element alpha in I, this set A alpha itself is either finite or countable. Then we have to prove that if we take the union of all the A alphas as alpha varies over I, then this set is also at most countable. And as a consequence of this, we have to also show that when I is countable and each A alpha is countable, then this union is countable. So let's see how we can have a solution. So we start off by showing that the union of two at most countable sets is at most countable. So let x and y be at most countable. That means each one of them is either finite or countable. If x and y are finite, then their union is also finite, and it's just a property of finite sets. Precisely this result. It will be proposition 3, 6, 14. Which part that I don't remember, I have to see it here. Y 3, 6, 14, part B. So when both the sets are finite, then so is their union. If, on the other hand, x and y are both countable, then their union is also countable. And this also we have already proved. It follows from proposition 8, 1, 10. So that means we are left with the two cases where one of them is when x is finite and y is countable, and the other one is when x is countable and y is finite. Obviously, it's enough to consider only one of these two. So we are going to consider the case where x is finite and y is countable. Now, let x be finite and y be countable. Suppose the cardinality of x is 1. This of course is not the general case, because the cardinality of x being a finite set can be any natural number, but we are specifically going to look at this case and see what we get, and then from that we are going to handle the general finite case. And because we are assuming that the cardinality is 1, so there will be precisely one element in x. So let that unique element be x. Also, our hypothesis that y is countable implies that there is a bijection between y and the set of natural numbers. Choose a bijection, say f, say. Okay, now define the map G from, but before I define this map, I need to say something else. It may happen that this unique element is actually inside y itself. That may happen because x and y are just some sets. If x belongs to y, then x union y is just y, which is countable. So in that case we need not do anything else. So assume that x does not belong to y. Now we are going to define that function. Now define the map. We need not write the map, because this is the map G from the set of natural numbers into x union y by this rule. G of n is defined to be equal to x if n is 0, and g of n is defined to be equal to f of n minus 1 if n is a positive natural number. And it turns out that this G is a bijection between n and x union y, proving that x union y is actually countable. But I am not going to prove that this G is a bijection. I leave this to you. However, I will in fact show the situation with a picture that will show you that it is really easy. I mean, in this form we may not be able to see it that clearly, but the situation is like this. You see, originally we had this bijection f, so that means the elements of y can simply be listed as f of 0, f of 1 and so on. So now what we are doing is this. This is our n. This is our n, the set of natural numbers, and this is x union y. So what actually we are doing is that we are listing the elements of x union y like this: x, f of 0, f of 1, f of 2 and so on. And we of course also have the natural numbers 0, 1, 2, 3 and so on. So we have mapped 0 onto x, then 1 onto f of 0, 2 onto f of 1 and so on, and it goes like this. So in showing that this G is a bijection, you have to of course use the definition of G and also the fact that this F is a bijection between N and Y. So this part I leave to you. So in this case what we have ended up proving is that X union Y is countable. So I'm just simply going to write like this. Show that G is a bijection. Thus, X union Y is countable. That means what we have actually shown is that if we take the union of a countable set and a singleton set, whether the unique element in the singleton set belongs to the countable set or here or does not belong to the countable set, it does not matter. The union is going to be countable. In this case also it is going to be countable. In this case which is Y itself, then also it is countable. So that's what we have shown. If one of the sets is singleton and the other is countable, then the union is countable. Now, using this, a straightforward induction on the cardinality of X, one can show that X union Y is countable if X is finite and Y is countable, and which I am not going to do, but still I am going to do it briefly. I mean at least I am going to show how to proceed. So you have to prove this thing and the induction should be applied on the cardinality of X. Since X is finite, the starting value, the base value should be 0 actually, because that is also allowed. So when the cardinality is 0, then X is the empty set. In that case, X union Y is definitely Y. So it is countable. So that means this is the basis for our induction. Then as induction hypothesis, you assume that this statement is true for any sets X and Y where Y is countable and X is a finite set whose cardinality is N, where N is some arbitrary but fixed natural number. Then you let X prime be a finite set whose cardinality is N plus 1 and let Y prime be a countable set. Then using a previous result about finite sets, you can then choose an element, say x. Do not confuse this x with that x, that thing is over, in x prime. So what that previous result says, that once we choose one such element in x prime, then removing x from x prime results in a set whose cardinality is of course n, one less than the cardinality of x prime. Then what you do when you consider the, let me show it here clearly. When you now consider the union of x prime and y prime, this is just simply clearly this union this one. Now this union is countable. This is countable by induction hypothesis because this cardinality is n. And this is countable by what we have proved just now, because here we are taking the union of a countable set and a singleton set. So we have again got two countable sets, so their union is countable by our previous this proposition 8, 1, 10. So that's how, using this induction argument, it then follows that for a general finite set x and a countable set y, x union y is countable. Similarly, x union y is countable if x is countable and y is finite. That means we have now covered all the cases. What are the cases? Namely, that when x and y are both finite, in that case their union is finite and hence by definition at most countable. Then that other case where x and y are both countable, then x union y is countable and hence again by definition at most countable. And these two cases where one of them is finite and the other is countable, in this case also the union turns out to be countable and hence at most countable. So we can write hence the union of two at most countable sets is at most countable. But why are we looking at two sets? That's because this will itself give rise to another induction argument where now we will be able to take any finite number of at most countable sets in an extremely straightforward way. Using this fact, we are now going to say, you can just simply proceed somewhat like this for the next thing. So which is this, using this it follows by induction on the cardinality of the index set itself that our actual original set is at most countable if I is finite. How exactly? I said somewhat like this induction argument. It's just simply this. Say you have one at most countable set. Then that union is just this set, which is at most countable. If you have n number of at most countable sets, say their union is at most countable. So this is at most countable. Then if you take another at most countable set, then your union will have n plus 1 sets. That will also be at most countable, because in that union this part will be at most countable by your induction hypothesis, and you have already proved here that the union of two at most countable sets is at most countable. So that's why this would be at most countable. So we are actually done proving the main claim of this exercise when our index set I is finite. That means when the number of A alphas involved in this union is finite. Okay. Now we go to the case where I is infinite, but since it's given that I is at most countable, that means assuming that I is infinite is just simply it means that I itself is countable. Now suppose I is countable. Without loss of generality we assume that I is equal to n. Okay, how can we make this assumption without loss of generality? That's because you see, what is the purpose of I? The purpose of I is just to label the sets that we have in this union. So if you are considering I, where now we have this supposition that I is countable, then choosing I is as good as choosing n. But still it sounds somewhat vague. Precisely, it is this. We are looking at this union, right? We want to prove that this union is at most countable. Now, since we have a bijection between I and n, the alphas themselves can be represented in terms of natural numbers. That means because you will have some sort of bijection, say H, between n and I, this union can be written as A Hn. Do you see this? Because as you vary n over n, the Hn actually varies over I as alpha. So we can in fact just simply assume that I is n itself. Really I may not be n, but some countable set. However, for our purposes, it's enough to consider that I is n. We don't lose any generality by assuming that. Okay. Now the original sets A alpha that are there in this union, they may intersect one another in any manner. I mean, anything can be there. However, we are now going to replace these A alphas with some other sets, B alphas, which are going to be mutually disjoint. They will not intersect one another. We now define the following family of sets, and that disjointness of those new sets will be used essentially in our next part of this solution. We now define the family of sets B alpha, also indexed by I, recursively as follows. The definition of B alpha is recursive, and the definition is just this: B0 or B0 is defined to be equal to A0 itself, and then Bn plus 1 is defined to be equal to An plus 1, from which we are removing the union of all the previous AIs. That means this: for all n belonging to the set of natural numbers. This is a well-defined recursive definition. Okay. Now what we are going to do, we are now going to prove that these Bn's, of course, the way we have defined these Bn's, they are going to be some sets like the An's. And we can now quit calling the A alphas, we can call them An because we have assumed I to be equal to n. But now what we are going to show is that this union of all the An's actually equals the union of all the Bn's. And this fact will enable us to replace to forget thinking about A alphas, because ultimately we are concerned about the union. So we can then think of the Bn's themselves. Let A be the union of our An's. Our this assumption makes this meaningful, and let B be the union of all the Bn's. We shall now show, let me just switch on the fan for background noise. Some program, some function is going on in the background, so some little noise is there. So to drown that out, I am going to use the ceiling fan. We shall now show that B is equal to A. Okay. Now B is equal to A. We can immediately see one thing from the definition of the Bn's is that each Bn actually is a subset of An. You see, this is how B0, of course, is equal to A0. What is B1? B1 is A1 minus A1 difference A0. What is B2? B2 is A2 difference A0 union A1. and then B3 accordingly will be A3 minus the union of A0, A1 and A2. So at each stage we see that it's after all a subset of A1. This one is a subset of A1, this one is a subset of A2 and so on. And this observation actually is a fact. In general, each Bn is a subset of An, which if one wants, one can prove by induction. One can prove, which will be extremely easy. It will follow almost immediately from the definition itself, but still in order to be rigorous, we are going to write like this. One can prove by induction that Pn is a subset of An for all natural numbers n. So as a consequence, the union of the Bn's, which is B, will also be a subset of the union of the An's, which is A. So hence B is a subset of A. Now we are going to prove the reverse inclusion, that A is also a subset of B. So for that we are going to choose an arbitrary element in A. Let A belong to A. Suppose that A does not belong to B. Excuse me. Contrary to what we are trying to show, suppose that A does not belong to B. Suppose that A is not in B. But since B is just the union of the Bn's, this supposition means that A belongs to none of the Bn's. So A does not belong to Bn for all n, for all natural numbers n. Now using this thing, this final conclusion, we are now going to show that A actually also, as a consequence, does not belong to any An either, which will be a contradiction because we have chosen A from A. So A must belong to at least one An, and that itself we are going to prove by induction again on n. Note that A does not belong to A0, which is B0, which comes directly from this condition that A does not belong to any Bn. Suppose that A is not there in Ai for all natural numbers I less than or equal to n, where n is some natural number. Okay. Now because A belongs to none of these Ai's, so A will also not belong to their union, then A does not belong to the union of the Ai's as I varies from 0 to n. Okay. Now in this situation, if A belongs to capital An plus 1, oh, this is, it does not belong to, okay. Now if A belongs to an plus 1, then by the definition of bn plus 1, a would belong to bn plus 1, because bn plus 1 is the difference of an plus 1 and this union. So if a is here but not here, then a would have to belong to bn plus 1, but that would contradict this condition that a belongs to none of the bn's. So we write which is a thus we must have that A. So the contradiction arises from what latest assumption? This. So that cannot be true. So A does not belong to an plus 1. So now you see that we can apply induction. In fact, we are using the strong induction principle. So this is our basis that A is not in A naught. This is our induction hypothesis, and this is the induction step where we have shown that A also is not in an plus 1. So by the principle of strong induction, A is not there in any an, and that is a problem. A does not belong to an for all natural numbers n. But this contradicts the very choice of A. That means A is being an element of A. So what went wrong? Namely, the supposition that A is not in B. That is the root of all problems. So the supposition E does not belong to B is wrong, i.e. we must have that A belongs to B. So, but A was an arbitrarily chosen element of capital A, so capital A is a subset of B. But we already saw that B is a subset of A, hence A is equal to B. Due to this fact, we can now work with B, because which is just simply A, but B is the union of all the Bn's, and the Bn's are mutually disjoint. For that fact, we now have to mention. One can prove by induction that Bn and Bn plus 1 are disjoint. It's easy to prove this one first, and it's easy means you have to do it. I won't do it here. It will follow immediately from the definition of the sets Bn. This is empty, and you can just simply see what I am talking about if you write what Bn plus 1 actually is. it is an plus 1 difference this, whereas what is bn is an difference this. Now, so do you see one thing immediately, that Bn is, in fact we have already seen this, Bn is a subset of An. That means you have An here, so this is your An, and Bn sits inside An, whereas Bn plus 1 is obtained from An plus 1 by removing the elements of A0, A1, and among them in particular we are also removing the elements of An. So no element of An is in Bn plus 1. In particular, the elements of Bn also will not be in Bn plus 1. As a result, these two are disjoint. And using this, one can prove that Bn and, in general the Bn's are disjoint. Bn intersection Bm is the empty set for distinct natural numbers n and n. Exactly how one can transition from this n plus 1 case to general nm case, see the solution to exercise 661. You go to this exercise, see what it's about. It involves something about sequences, but looking at how the solution was obtained, you will realize how one can make this transition. Okay, so we let it sit like this. We have replaced the A alphas, or now ANs, by Bn, which are now mutually disjoint. Let's end this paragraph by concluding like this. Thus, the Bn's are mutually disjoint. Fine. So we have replaced the ANs by Bn's. The thing is that we can now use them because their union is also equal to the union of all the ANs. But how are we going to use them, and where shall we exactly need this mutual disjointness? Now we are going to see. Now the thing proceeds like this. Let P be the set of all prime numbers in the set of natural numbers. Usually when we say the set of prime numbers, it just simply means this, but I want to be more absolute about this. Okay. Now, the fact we are now going to use about P is that P is countable, and we will get that by using two results. One of them is that P is a subset of N. So by a result from our studies here in this text, P would be at most countable. But the other result is that P is infinite. There are infinitely many primes. So that is why P has to be countable. And those two results are these. by theorem 3.4 from David M. Barton's elementary number theory, which is just the statement that P is infinite, that there are infinitely many primes, Euclid's statement. And corollary, why suddenly we are bringing in prime numbers, you will realize they will become very convenient. And our corollary 816, which says that any subset of the set of natural numbers is at most countable. P is countable. So we can choose a bijection B from N onto P. Okay. Now for each natural number N, we are also going to define some subsets of the set of natural numbers. For each N belonging to N, consider the set Cn, and Cn is this. So that we don't lose track of what is going on, let us see what we have done so far. We have considered the set of all prime numbers. Due to it being a subset of N, it is at most countable. But additionally, since it is infinite, which we know from number theory, it will be countable. So there will be at least one bijection like this. Fine. Simultaneously, for each natural number N, we are considering the set Cn. What are the elements in Cn? The elements in Cn are positive integral powers of B of n, and this B of n are actually what? They are nothing but the prime numbers. B of 0 is the, we don't really know whether, in what order these primes will appear. That will be determined by this bijection B. But if this bijection B happens to list the primes in their natural order, that is how they appear on the number line. Say the first prime is 2, then B of 0 would be 2. So C of 0, C0 or C0 would then be, in that case, all the positive integral powers of 2, where the exponent is a positive integer. So precisely these numbers 2, 4, 8, 16 and so on. Similarly, C1 would be the positive integral powers of 3, then the positive integral powers of 5, 7, 11, 13 and so on. It does not really matter that we should take, if you want, you can take the natural order in which the primes appear, but I wanted everything to be rigorous. Anyway, so now we have these sets Cn. Okay, now some facts are there about these sets. By corollary 569e, this is the corollary that gives us the rules of exponents. We have already seen this thing. And corollary 2 to theorem 3.1 from again Barton's elementary number theory. Which we indicate by writing Barton within brackets. From these two results, we get this fact that the sets Ci are just like the Bi's mutually disjoint. At once it seems like something really difficult. However, once you note that what we have here are nothing but the prime powers, it becomes clear why they are disjoint. For example, some Cn would be these, the powers of 2, and some other Cn would be, say, the powers of 7, or say the powers of 11. Can there be anything common between two such distinct Cn's? Of course not, because they are powers of different primes. And the fact that they are not the same, that is justified by these things. This corollary, which gives us the rules of exponent, makes sure that the powers stay distinct. And this one, I don't exactly remember what this thing says, but you need not worry. You can just write your own, for this part, you can write your own justification for why two such sets will never have any common element. And it has something to do with prime factorization of an integer. You understand what I am talking about. So that is why they are disjoint. Okay, but let us now go back to the Bn's. We have already noted that each Bn is a subset of An, and the original An's are what? They are all given to be at most countable. So each Bn is also going to be at most countable. If An is finite, then Bn is going to be finite and hence by definition at most countable. Whereas if An is countable, then Bn is either finite or countable. That means again at most countable by the results we have so far obtained in this section. Now, being at most countable means what? We are able to find an injective function, some sort of injective function from Bn to n. And this fact we have already proved, that if we have an at most countable set, then we can find such an injective function, and conversely, if there exists an injective function like this, then this set has to be at most countable, again in one of the results we have obtained so far. So that fact we are now going to use. Since each Bn is at most countable, there exists an injective function Bn from Bn into, oh, what, I brought in complex numbers, Bn into n. Okay. Now we are further going to define some functions from each Bn into Cn, but before that I need to mention something else also. Note that here we are doing what? The result that we are using here says that due to the utmost countability of Bn, such a function exists, such an injective function. Maybe there are multiple such functions. We don't really know how many such functions are there, but at least one function is there. And how many Bn's are there? Countably many, infinitely many. So it's like you have infinitely many boxes from which each one of which you are picking one injective function Bn. And this, strictly speaking, needs the axiom of choice, about which we are going to see it's coming. It just simply roughly says that if we are given any number of non-empty sets, then from each one of them we can choose one element. It's just that. We need the axiom of choice here. It's an extra axiom that needs to be included in Zermelo-Fraenkel set theory, that makes it Zermelo-Fraenkel choice set theory, ZFC or ZFC. Okay, so now we are going to define some specific functions. We now define the functions. All of these seem extremely convoluted and unnecessary, but they are necessary. We are going to see why, how. The functions Kn from Bn into Cn by these formulas. Kn of j is defined to be equal to B of n to the power Bnj plus 1. Okay, we now need to understand how these functions Kn are well defined. Do they make sense? Let us try to see. We keep in mind that we already have these Bn's. Okay, and what was our original function B? The function B helps us label the prime numbers in some order. So in this power, the base B of n is actually a prime number. And in fact, this B of n belongs to Cn. Why? That is because according to the definition of the Cn's, Cn is this. Okay. But we do not have just simply Bn here, but rather this power of Bn. The first thing to note here is whether this output belongs to Cn or not. That is the first thing. It looks like it belongs to Cn because it has the same structure. But is this exponent a positive integer? It is, because you see what is our bn. B of n, I mean the function bn maps bn into n. So this bn of j is some natural number. It may be 0 also, but to make it positive we have added 1. So this output actually belongs to Cn. Now again there is another question: is this unique for a given j? The functions bn themselves are well defined. So for a given j in bn, this bnj itself, just simply this bnj is a unique natural number. So if you add 1 to it, that exponent is going to be a unique positive integer, and as such this power is a unique element in Cn. So that is why each Kn is well defined. So we are going to now write the fact like this. We will just simply write clearly each Kn is well defined. But something else is also true. Each Kn is not just well defined, but is itself an injective function. Let's see how. To see it directly, we just take two distinct elements in Bn. Say j and j prime in Bn. This I am not going to make a part of the solution because one can just simply verify it. J and j prime in Bn such that j is not equal to j prime. Now note that this Bn, this function is injective. So distinct inputs imply we have distinct outputs. As a result, Bn of j plus 1 is also not equal to Bn of j prime plus 1. And as a result of this, these powers of B of n are also distinct. That means Kn of j is not equal to Kn of j prime. That just simply says that each Kn is injective. So we just simply write like this, and injective. We are doing all these things with bringing in prime numbers and whatnot for having this injectivity. If you want, you can do something else also. And injective. We do, however, include this mention. Note that each Pn is injective, and this fact has been used in concluding that each Kn is injective. Now using these Kn's, because defining these functions is not over yet, we still have to define some other function. Now define k from p into n by k of j equal to Kn of j if j belongs to Bn. Note that finally now we are looking at a final stage, sort of, where we have defined a function from B into the set of natural numbers. Now this part we have to understand carefully. So what we see here is this. Let me draw a diagram for this. This is our B, inside of which we have the Bns, and keep in mind the Bns are mutually disjoint, and now we need this mutual disjointness. Say this is B0, this is B1, B2 and so on, right? There are other B's. So now what we are doing is this. We are of course going to choose some input from B. Now that input will lie inside B in some Bn, and due to the mutual disjointness of the Bn's, that J will lie in exactly one Bn and not simultaneously in two different Bn's. Say that J lies here, then it will not lie here or somewhere else. Now the moment J lies in B2, K of J by definition is just K2 of J, and this K2 is itself a well-defined function from B2 to C2. But note that because each Cn after all is a subset of the set of natural numbers, the final image is going to be a natural number. It will be a power of some prime, but after all it's a natural number, and in fact a positive natural number. So that just tells us that K is well defined. Why is it well defined? First of all, for this input J, the output is a natural number because it's lying in Cn. Is that output unique? Yes, it is unique, because Kn itself is a well-defined function. So for a given J, Kn of J is going to be a unique natural number, and the fact that this n does not change comes from the mutual disjointness of the Bn's, and this n in fact will be determined by where J lies. That is why K is well defined, and these functions becoming injective, that is going to now be transferred to K as well. So let me now continue. Let me keep this Kn of J for now, and let me continue from here. The function K is well defined because each Kn is well defined, or let me write it in this order because the mutual disjointness comes first, because the Bn's are mutually disjoint and the Kn's are themselves well-defined functions from Bn into n after all, and additionally K is injective because of a similar reason, because each Kn is injective. This injectivity part we need to see a little more closely. I will need to draw B again, but slightly differently now. So this egg is B, and here we have, say, two compartments. I mean two BNs. Then this is BN and this is BM. Now our aim is to show that this K is injective. So what we do is that we are going to choose two distinct elements in B, two distinct inputs for K, and show that the outputs are different. So let those two inputs be I and J. Now there may be two cases. There will be two cases. One of them, I and J lie in different B's. Say I lies inside Bn and J lies inside Bm. Each Kn is O. And I need to also mention that. And the Cn's are mutually disjoint, because otherwise their disjointness need not have been mentioned. So now say this is our situation. I and J belong to distinct BIs. Then according to the definition, what is going to be Ki? Ki is going to be Kni. And this, by the definition of Kn, is going to lie in Cn. And this, of course, all these things are in N. So this I is going to be mapped here. Similarly, because J is coming from Bm, and by definition K of J is Km of J. So this thing will lie inside Cm. And because the Cn's are mutually disjoint, so the outputs they must be distinct. That is one case. And the other case, let me draw another diagram for the other case. In the other case, we have both I and J inside a single Bn. Fine, but they are of course distinct. However, now what is, again just like before, Ki is Kn of I, but now Kj is also Kn of J. Now because Kn itself is, I got rid of the Kn, but anyway you understand, but because each Kn itself is injective, these two are going to be distinct. That is, this is Kn of I, this is Kn of J, so they are not going to be equal. So in any case, the outputs of I and J under K are going to be distinct if I and J are distinct. So that is why K is not just well defined, K is also injective. But what have we obtained then? We have obtained a function K from B into N that is injective. But that tells us what? That just simply tells us that B is at most countable. But B, we have already shown that B is nothing but A, the union of the original An, so that is at most countable. So that is how we have this conclusion. mutually distant. So ideally we should start from here. So now I continue. Hence A, which is nothing but B, is at most countable. But we are really not over yet, because there is that other extra part in the exercise which asks us to show that when the index set I is countable and when each A alpha is countable, then the union is countable. But for that you just need to see this, that A, which is the union of all the original A alphas, is at most countable by what we have proved. But A contains A naught or some particular A alpha. Now we have gone back to the absolute generality, where we just have a countable set I, not necessarily N, the set of natural numbers. So A contains each A alpha as a subset. Now because it's given that each A alpha is countable, that means each A alpha is infinite. So A also has to be infinite by the properties of finite sets. At most countability of A and the fact that it's infinite then implies that it has to be countable. That means if I is countable and each A alpha is countable, then their union is also countable, and this is where the exercise ends. There is one more exercise in this set where we will be asked to give a concrete example of a bijection between N, that is the set of natural numbers, and the set of rational numbers. Recall that we have already proved that such a bijection exists by proving indirectly that Q is countable. However, it just simply means that there is a bijection. Can we actually find a bijection? That is the next exercise, which we are going to solve in the next analysis video. So I just end things here itself, and the next video is this coming Tuesday. So because we have already gone through group theory once more, so let us, what shall we do? Let us do calculus on Tuesday. So that's just it. I wrap things up tonight. So see you on Tuesday with calculus. Until then, this is me, Lucifer, from A Mathematical Room. Have a nice day.